Everybody. Today we are discussing the ring flipping, the second part of the cyclohexane. So in the last class we have discussed the conformations of the cyclohexane and what is the important conformation of the cyclohexane, why the chair form is more stable, and axial and equatorial bonds. Now today we are discussing how the chair form is converted into another chair form, and these two chair form are exist in an equilibrium, and this conversion occurs at room temperature itself. So the first one is the chair form, and here the position of the one, there is an axial and equatorial bond. During flipping, the carbon, the position of the first C1 carbon atom, they changed their position, and also the axial bond of the C1 carbon become the equatorial bond now, and equatorial bond become axial bond now. See here I have shown the red color hydrogen for the C1 carbon atom, that is an axial equatorial form in the left hand conformation of the chair form, whereas in the right hand side it is in the axial position. So this is mainly due to the flipping. So on flipping, the C1 carbon atom uh, is in the upward direction in the first chair form, and in the during flipping the first C1 carbon atom is in the downward, and whereas in the C4 carbon atom in the first conformation is in the downward, during flipping it is in the upward. So this process occurs in a very short interval of time, that means the ring flipping is occurs at room temperature itself. So during flipping the axial bond is converted into equatorial bond, and similarly the equatorial bond is converted into axial bond. Now what are the other conformations of the stable conformations of the cyclohexane? So we have studied the chair form, board form, and the second is the half chair. Half chair, this is the structure of the half chair, and the fourth form is the twisted board. So how we have already discussed that one of the chair form is converted into the other chair form. So the ring flipping occurs in cyclohexane very rapidly. So how this ring flipping occurs and what are the conformations are present during this ring flipping? So first of all, this chair form is converted into the half chair, and this conversion is exist in an equilibrium. So during the conversion of the half chair into the during this conversion from chair form into half chair, you know that the for the chair form it is devoid of angular strain, steric strain, and torsion strain, whereas the half chair have the torsion strain and also the steric strain and angular strain. So all these strains are exist in the half chair. This is mainly due to the existing angle, it is deviating from the tetrahedral bond angle, that's why it acquire the angular strain, and the end of the half chair are very much closer when compared to the chair form, that's why it acquire torsion strain, and it also acquire the steric strain. And this half chair conformation is readily converted into the twisted boat. For the twisted boat, it is lack of it have no angular strain, since it acquire the bond angle of the tetrahedral bond angle, and it is also lack of the steric strain, because in the twisted boat the both end of the boat is maximum distance apart, and so it is devoid of the torsion and steric strain, and it is again converted into half chair. But see here the half chair, the position of the half chair is entirely different, which are opposite. Then it is again converted into the chair form again, but here also the chair form, the position of the carbon atom in the both the chair atom are different. So this is the mechanism of the ring flipping, and during this mechanism axial bond is converted into equatorial and equatorial bond is converted into axial, and this ring flipping is occurs through these conformations of the cyclohexane. Now, this is the potential energy level diagram of the cyclohexane. For the potential energy level diagram, we should mention the energy in the y-axis and the rotation or conformation is in the x-axis. So, before in the 0 degree angle, all the molecule or the ground state, all the molecule are exist in the chair form, and chair form is devoid of angular strain, torsion strain and steric strain. So it is exist in the 0 level of the 0 coordinate, and it is converted into half chair. We are already told you that the half chair having the angular strain because it is deviating from the tetrahedral bond angle, torsion strain and steric strain. Then it is converted into the twisted boat, and twisted boat is devoid of angular strain, steric strain and torsion strain. Then again it is converted into boat form, and again it is converted into another twisted boat, and you know that the twisted boat energy of the twisted boat is very lower than that of the boat form. Then again it is converted into half chair, and it is readily converted into the chair. So this is the mechanism of the the ring flipping, and see here the energy positions of the conformation of the cyclohexane. So most stable conformation of the cyclohexane is the chair form, which is exist in the x-axis, actually touching the x-axis. And the least stable conformation of the cyclohexane is the half chair. It acquire the angular strain, torsion strain and steric strain. So that's why the half chair have the maximum energy. And for the twisted boat, it is also less energy than that of the boat form. This is the potential energy level diagram of the cyclohexane. Now is another important question, the conformation of the methyl cyclohexane. Methyl cyclohexane means we have already studied the cyclohexane. The stable conformation of the cyclohexane is the chair form. If you are replacing one of the hydrogen by using the methyl group, what will happen? So there are two possibilities exist in this methyl cyclohexane. One is the methyl group are arranged in an axial position, or it can be arranged in the equatorial position. Which one is more favored? If the methyl group are exist in an axial position, see in the figure, we can see that the hydrogen of the methyl group and the hydrogen which is exist in the third and fifth position are very much closer. So that's why there is a repulsive interaction is existing, and this interaction is known as 1,3 diaxial interaction, because the 3 and 5 CH sigma bond is very much closer to the or very much parallel to the molecular axis. That's why it is known as 1,3 diaxial interaction, and this interaction is very high in the methyl group which is exist in the axial position. So that's why methyl group is exist in the equatorial position. If it is in the methyl group exists in the equatorial position, it is devoid of any of the strain. That's why the stable conformation of the methyl cyclohexane is in the equatorial form. So the both the question today we have discussed is very important. First is the second part of the cyclohexane, potential energy level diagram and ring flipping, and the methyl cyclohexane is also very important. Hope you understand the concept. Thank you.